Hello, my name is Joe Webster. I'm a graduate student at the University of Oregon, and this talk is about the p-adic Mehta integral. We want to start with something that has already been done, but it's really good for context. So, a statistical model for electrostatics on a line. The setup here is we want to consider n labeled point charges with random locations, say x1 through xn in R. So this is on a line. And we're going to collect those into a tuple called bold x. And these tuples are going to be called microstates. So what you want to imagine is that the system is randomly changing between various microstates. For each microstate, we're going to assign a total energy E of x. And this E can be any measurable function you like that goes into the extended reals. And it really just depends on which model or which application you're trying to work on. So you get to choose the energy. We're also going to assume that the system is in thermal equilibrium with a heat reservoir at absolute temperature T greater than 0. Now this is a temperature that the system is sort of submerged in. The energy is allowed to change with X, but in doing so, it doesn't change the temperature around it. This is what the thermal equilibrium ensures, and it's really just something to make sure that our temperature is not depending on our energy. We're going to fix a constant k greater than 0 that makes the energy over kT dimensionless. So this really just serves a purpose of making that ratio something that we can plug into other functions, such as exponentials, as we will. And with that k in hand, we're going to define the inverse temperature parameter, beta. And really, this is just a notational convenience. It'll be nice to work with beta instead of T moving forward. The key idea here is that the energy we picked induces a probability distribution on the microstates. So what we want to do, as I said, is raise E to the minus beta times the energy. This is the same as negative energy over kT. Because that is unitless, we can do this. So by summing up all of these exponentials or integrating them, we get a total mass, and we divide that out to make it so that this is a probability density. Notice again that this is completely determined by the energy, and the density itself varies with beta. The intuition here is that if microstates have low energy, then they're going to be more likely because that exponential will be larger. Higher energy states, on the other hand, will be less probable. And one thing to notice is that as T gets closer to 0, so as the system gets colder, this beta here gets larger. And that means that this decay rate is more severe. That means that high energy microstates are going to be especially unlikely if the temperature is low, and vice versa. The practical use of this probability distribution is that you can take expectation against it and learn about the observable or macroscopic behavior of the system, especially in terms of temperature. So you can understand how the system will change in a very observable sense as the temperature changes. So this is kind of the root of that relationship. And with that in mind, I want you to consider the fact that having a explicit formula or an explicit formula for Zn of beta is really handy here because it makes that distribution explicit. And once you have that, you can actually compute expectations against it. So if there's anything I want you to take away from these first two slides, it's that knowing this canonical partition function, as it's called explicitly, is really, really important for doing problems of this kind. The particular one that has motivated this talk is the Mehta integral. And this is a canonical partition function. You want to understand this integrand here as e to the minus beta times an energy. And that energy, in this case, is exactly the sum of n harmonic potential energies and n choose 2 log-Coulomb potential energies. Each of them plays a separate role. Notice here that the harmonic potential energy gets larger, the ith one that is, gets larger if xi is far from the origin. So if the ith particle gets far away, it makes the energy larger, makes the total energy larger, and therefore it gives you a less probable microstate. Similarly here, if two particles xi and xj are close together, then this logarithm will be a large positive number and will make the total energy larger. So if particles are close together and or far from the origin, then you're going to have a high energy microstate, which has low probability. In other words, having particles far from the origin or close together is probabilistically punished. This integral showed up in random matrix theory in the 60s. It's named after Mehta because of this. Dyson and Mehta realized that this was actually the normalization for a probability density function that determines how the eigenvalues of certain random matrices are distributed. In particular, if you have a Gaussian orthogonal ensemble of matrices, then its eigenvalues x1 through xn will be distributed according to this density. If you have the unitary Gaussian ensemble, then beta will be 2, and the eigenvalues will be distributed accordingly. And when beta equals 4, that corresponds to the Gaussian symplectic ensemble. So this one integral is important in random matrix theory at those 3 specific values of beta. After computing it for those values, they realized that this might be the explicit formula for this partition function. And they were able to determine just by looking at the integral that it would converge and be holomorphic for such beta. So that is beta with real part greater than -2/n. However, they only knew at the time that the integral equaled this quantity here for those particular beta. Fortunately, about 10 or 15 years later, Bombieri turned this conjecture into a theorem and showed that it's actually true for all the beta that they wanted. So this also contributes something to the physical perspective, because now, in particular for beta greater than 0, real beta that is, you can actually compute expectation against the probability density we mentioned on the previous slide. What we're going to do today is establish an analog for this formula when the field R is replaced by the p-adic field. So let's set that system up. P-adic log-Coulomb gas. Here we have charges now with random locations in QP. So this is instead of R. And accordingly, QP to the n becomes the space of microstates, which are again the tuples. And now instead of the Euclidean norm, we have to define a different norm. This is the standard for QP to the n. And really, one of the main reasons that this is the standard is it preserves the strong triangle inequality, which is something that the p-adic absolute value satisfies. Here we're also going to have a Haar measure, and it's going to be normalized to give Zp to the n measure 1, where Zp is the ring of p-adic integers. It's convenient also that the p-adic integers are the closed unit ball in QP. Now we have to define our energy function, and we're going to define it very analogously to the one that was involved with the original Mehta integral. So here we need to choose some v of x that makes up for the harmonic potential part. Now I'm not choosing this particular function here because this norm is not Euclidean. So it does not play with squares and sums of squares the same way as the Euclidean norm does. Still, we can insist that v is some choice of a function where this exponential, e to the minus beta times v, is something that depends only on that norm. So notice that that was the case for the Gaussian part in the classical setting. So we're just going to choose a nice analog. Of course, in the word nice here, I'm including some extra things about the decay of rho and some boundedness conditions near 0. We're not going to worry about what those are in particular. Just trust that from now on, rho is a nice enough function, much in the way that the Gaussian is nice on Rn. Okay, so that handles the harmonic part, or the analog of the harmonic part. And now we just have pretty much word for word the same sum of log-Coulomb potential energies. But here, the distance is measured in the natural way with the p-adic absolute value because these are p-adic numbers. All right, so there is our total energy. And if we take that energy and multiply it by negative beta and exponentiate that, then we get this integrand. And the question for today is, what is the explicit formula for this canonical partition function? So this is the p-adic Mehta integral. We want to know what it is. And more than that, we want to know for which beta it converges. So we're going to take advantage of some very nice facts. One of them is that we actually don't need to compute this integral as is. We can reduce it to computing this one. And this has something to do with the fact that this Vandermonde polynomial inside the absolute value, note that we can pull the absolute value bars outside of the product. That polynomial inside is homogeneous. And what that means is you can cut up this domain qp to the n into shells on which this norm is constant. In other words, the sphere is in qp to the n. And using those shells, you can pull out some factors, and the homogeneity, of course. You can pull out some factors and rewrite this thing as a sum of other integrals. And the common integral that we just mentioned is going to show up here. So that was a long way of saying that computing this really just comes down to knowing what this bracketed function is. And this is where all of the dependence on rho goes, and knowing the value of this integral here. So we're going to spend the rest of the talk just trying to figure out what this integral is. Nice fact 2 is if we look at the subset of zp to the n, so we're now looking inside our integration domain. If we look at the places where any of the entries in this tuple are equal, that actually has measure 0. And that is very much like the case in Rn. This is really fortunate because when we integrate over this, so if we take zp to the n and remove v0, it's not going to affect the value of this integral. Now I want to take a moment to figure out what elements look like in this thing. So if we take zp to the n, remove all the bad points, all the ones where particles are in the same spot. What do these microstates actually look like? So this is the fun part. All right, so it's convenient to work with a particular prime here. So I've chosen the prime 3 because it makes the picture non-trivial enough and also visible enough, but it's not so large that you can't see anything. So 3 is a good prime for this discussion. Z3, as I said before, is a closed unit ball. So I'm just thinking of 9 particles in a closed unit ball. And keep in mind that since they are not in V0, none of the particles are on top of each other. They are all in distinct places. Okay, so how can we start to pick apart this microstate and understand what the log-Coulomb potential energy might look like? What I want to do is start filtering Z3 by higher and higher powers of 3. So if we look at this mod 3 to the 0, so if we essentially take every particle, remember this is every particle here is a p-adic number, we can mod it out by powers of 3. If we mod out by 3 to the 0, we're modding out by 1, and everything falls into the same class mod 1, so we don't really get any new information. Notice here that I have recorded this in a partition of 1 through 9. So these are the indices of the particles. And all I'm saying with this partition is things have not been distinguished yet. Now if we mod out by 3, what we'll notice is the 3 cosets of 3z3 form different containers around different parts or different groups of these particles. So notice that 5, 7, or the particles x5 and x7 are together in their own little coset. The same goes for 1, 2, and 9. The same goes for the rest in their own. If we mod out by 3 squared, or 9, just by chance, by the way I chose this example, notice that even though they find themselves in smaller cosets, they have not become any more distinguished. So 5 and 7 are still together, 1, 2, and 9 are still together, and these other 4 are still together in their own coset of 9Z3. If we refine again, modding out by 27, we see that 6 has broken away from its 3 friends, 3, 4, and 8, even though the others are still in the same cosets mod 27. And you'll notice I tried to squeeze some labels in here for the cosets. This is the last level where we're going to do that because they would have to get very small. All right, modding out by 81, we see that the particles are starting to become almost completely distinguished. The only ones that are still together, mod 81, are X3 and X8. So I've got that one part over here that still has 2 things in it. Modding out by 243, once again, we see that no further distinction between the particles has happened yet. So these are still together. But finally, when we get to mod 729, we can see that they are in their own little cosets, and all of the other particles are in their own cosets. So we finally reach the partition where everything is broken apart. And at this point, we don't really learn anything else. So we can still mod out by 3 to the 7th, but we're not going to learn anything new, at least as far as these partitions are concerned. So what does this diagram actually mean? How are we going to use it? So I want to think of this microstate as determining a pair of tuples. Really, what the point of that diagram was to show you those partitions. We're going to talk about those. So this pitchfork here is the tuple of distinct partitions that we saw. The 0th one is the trivial partition, and that appeared only once at the top. Pitchfork 1 was the next one that we saw, and that one appeared twice in a row. We saw this one only one time. We saw this one twice. And then this one appeared for every mod 3 to the n for every n greater than or equal to 7. So this was sort of the final one that was distinct. Okay, so what does this information say? Before I actually get into that, I want to point out that the prime p equals 3 is not special. As I said, it was nice for that example, but it's important to note that you can find many other values of x or many other tuples of length 9 in these different spaces, and they can still produce the exact same data we've got here. So you can cook up examples for any p greater than or equal to 3. So you can cook up x values like this that are going to generate the same tuples that we found here. So on that note, what I want to do is define for any prime p, including 2 this time. So for any prime that you want, I want to define t sub p of the pair pitchfork bold n to be the set of all microstates in zp to the 9 that determine this particular pair that we've got up here. So that is what TP of the pair is. It's a set of x values. Now the features of TP are the things that are going to be really helpful for actually doing the integral. The first is that it happens to be a compact and open set, and we know that we can take measures of such sets. The Haar measure of this set turns out to be this power of p minus 1 times the power of p minus 2 times this product of p raised to negative rank of a partition times the corresponding NL. So the rank of a partition, remember, is the size of the partition. In this case, it would be 9, minus the number of parts it has. So I think maybe it's useful to run back to that slide and just run through the ranks really quickly. The rank of this one is 8 because it has 9 things inside it and only one part. The rank of this one is 6. The rank of this one is 5. The rank of this one is 8. And the rank of this one is 0. Or sorry, the rank of this one is 1. And the rank of this one is 0. Okay, so we know how to compute ranks. We know what these NLs are. And just for fun, I figured I would throw in what this value actually comes out as for this particular pair. I don't really have enough time to get into where these p-1s and p-2s are coming from, so you'll just have to take those on faith for now. The next really useful feature of TP is that this Vandermonde polynomial, if we take its p-adic absolute value and x is any element in here, then we can also compute this in terms of only the pair pitchfork and bold n. So this is really, really handy because what it says, or what these two things say together, is that I have a set with an explicit measure, and I know that this function, which is the thing inside my integral, I know that this function is constant on that set. So immediately what we get, oh, I should add, I added this in for fun as well. That value is p to the minus 29. But what we get by combining these two things is that this integral over this set TP is just the product of the two things above. So, well, I kind of lied here. Really what we need to do is exponentiate this by beta. So we need to raise this to the beta power and then multiply it by the measure. So rearranging some of the factors, this is what you get for that integral. So we haven't exactly done the integral we wanted, but we have done a piece of it. We've integrated over a part of the domain that we wanted. And what we got was something that depended explicitly on pitchfork and math bold n, or I should just say bold n. Okay, and the punchline here is that if we sum over all of the possible pairs, I haven't said what all of these look like yet, but if we sum over all of them, then we actually get the integral we wanted. The thing that's really nice here is that this is a countable set. So there are only countably many pairs of this kind. So we know that this will actually just be a countable sum of integrals like this. And another thing that's really nice about each one of these integrals is it's an entire function of beta. So you can put any complex number beta you want here, and you'll get an entire function. You can check immediately that this is an entire function of beta. And when you have a countable sum of entire functions, it's much easier to work out when it converges and whether the resulting thing is still holomorphic. And it turns out, sort of as I've been leading up to it, that the value that we're going to get for the Mehta integral boils completely down to combinatorics. So these pitchforks that I wrote before, they have a name. They're called splitting chains. So the one we had before was a splitting chain of order 9. In general, a tuple of partitions of the set 1 through n is called a splitting chain of order n, and L here is the length. It's called that if the partitions in order strictly refine. So we have to start with the trivial partition at pitchfork 0, and then refine that down one step at a time until we get to the last one, which is the partition that is completely broken apart. Notice that every splitting chain of order n is going to have length at most n minus 1. So you know for a fact that the set of splitting chains of order n is finite. Okay, so we're going to write that set as Sn. And I want to note here that each splitting chain has something called a multiplicity polynomial. And this is a really nice polynomial, but it takes quite a bit, or it takes a more in-depth look at splitting chains to actually define it. So for now, I'm just going to say that it's monic in degree n minus 1. So it's a nice invariant attached to each splitting chain. And just to give it a little more context, that is where that p minus 1 to the 6 times p minus 2 squared came from that we saw before. So this right here is a multiplicity polynomial evaluated at p. Okay. Now using that, I'm going to attach to each splitting chain a rational expression in t and t to the beta. So just think of these as formal variables for now. And this expression here is rational in both of them. Note that this E sub pitchfork L is something we actually saw before. So it's really just shorthand for that quantity that we saw in that exponent before. So these new things that we're defining have some motivation. All right, so I've got some rational expressions, and they are determined by splitting chains entirely. I want to point out an important fact here. None of the things on this slide depend on the prime. So these things are purely combinatorial. Okay, and here we are at the theorem. So the Mehta integral, it happens to converge for exactly the same complex numbers that the original Mehta integral did, which is pretty interesting. And the value is given by this explicit sum. So we sum all of those rational expressions, evaluate them at p first, and then sum all of them. And we know that's a finite set that we're summing over. So this resulting sum here is rational in p and p to the beta. And then this bracketed term we already saw before is something that comes out of the original integral in our reduction step. So if rho is chosen to be nice, something like a characteristic function of the closed interval 0 to 1, then what we'll actually get is a rational function in p and p to the beta in the bracketed term as well. And this ties into things about local zeta functions that have been known for a long time. But I think I'm going to steer clear of that for this talk. All right, this is the last note. I just wanted to point out that this theorem is actually a corollary of something more general, where you can do the integral actually over k to the n, where k is any non-Archimedean local field. So QP is an example of such a k. Any finite extension of QP is also this kind of field. And also there are the Laurent series with finite field coefficients. So there are several kinds of non-Archimedean local fields. And it turns out that if you want to do an integral like this over any of them, or any n-fold copy of them rather, then you actually get a result that's very similar to the one above and implies the one above. On top of that, this max and min inside, those are kind of handy things to add because what you learn by doing an integral with various a and b is you get the joint moments for the diameter of the gas, which is this maximum, and the minimum particle spacing. Okay, so that is all I have to say for now. If you want to learn more about this more general result, please check out my paper that has been linked under this video. Otherwise, thank you very much for watching my talk.